Thank you, Mr. Chairman. Ladies and gentlemen, it's my pleasure to present our work on fully symmetric vertical Hall devices in CMOS technology. The outline of my talk is as follows. After a short motivation, I will introduce a state-of-the-art vertical Hall sensor and explain its drawback compared to planar Hall devices, which is their offset characteristic. Then I will introduce our novel approach to improve the offset behavior of vertical Hall sensors. We call it the fully symmetric vertical Hall sensor. Thereafter, I will explain in detail the experimental results obtained with fabricated state-of-the-art devices and our novel approach. Finally, I will conclude my talk. Among the various sensing technologies which are used to detect magnetic fields, the Hall effect is probably the most widespread. It is possible to construct high-quality transducers using standard IC processes and integrate signal conditioning circuitry on the same chip. As a first major application, Hall effect sensors were used to replace mechanical contacts in computer keyboards. Thereby, the reliability and durability of these devices were vastly improved. Nowadays, you find Hall effect sensors in automobiles for the ignition timing or the anti-lock braking systems. For absolute precision measurement, you need a 3-axis magnetic sensor. Combining a planar Hall device with vertical Hall sensors provides a multi-axis sensing capability. Thereby, the planar Hall device senses the magnetic field perpendicular to the surface, whereas two vertical Hall sensors aligned at 90-degree rotation to each other enable the measurement of the in-plane magnetic field components. The major drawback of the vertical Hall sensor structure compared to planar devices is the lack of a four-fold symmetry. In turn, offset compensation techniques are less effective, and our goal is to design a vertical Hall sensor with an inherent symmetry compared or equivalent to planar Hall devices to reduce the offset of these devices. A state-of-the-art vertical Hall sensor which can be implemented in CMOS technology is shown on the upper right. It's called the 5-contact vertical Hall sensor. The device consists of an N-well diffused in a p-dot substrate. It has 5 N+ contact diffusions, but you can consider the device electrically as a 4-contact device because the outermost contacts are short-circuited. The device works as follows. A current flow is generated between the biasing contacts, and when the device is exposed to a magnetic field perpendicular to the current flow, the equipotential lines are deflected and an output voltage is generated between the measuring contacts. As a 4-contact device, the sensor can be operated in 4 different modes. For each mode, the signal of interest, which is the Hall voltage, is superimposed by an offset which is measured even in the absence of the magnetic field. The current distribution in the 5-contact device as well as the offset is shown on the right, and an offset of about 3 to 5 millivolts is much larger than the Hall voltage you want to measure. To operate the device in the second mode, you just have to switch switch the biasing and sensing contacts. Again, the current distribution in the device as well as the offset is shown on the right. In contrast to mode number 4, the second mode has a more stronger quadratic contribution. The current distribution in mode number 3 is symmetric to mode number 1 with respect to the plane through the middle contact. In turn, the offset behavior of mode number 3 is similar to mode number 1. In contrast, the current distribution of mode number 4 is the image under reflection of mode number 2. And these different symmetries lead to the distinct offset behavior. So the quadratic contribution of mode number 4 in green is of opposite sign compared to mode number 2. To reduce the single mode offset, the current splitting technique can be applied. Thereby the average over all modes is calculated. In general, the technique or the effectiveness of this technique depends on the symmetry of the devices. So for a device with symmetric modes, a zero residual offset is possible. Although this graphical representation gives the image of a zero residual offset, it is still in the range of several hundred microvolts, which is equivalent to an offset of 2 or 3 millitesla. So to improve the symmetry of the devices and reduce thereby the residual offset after current spinning, we have to find the origin for the asymmetries in the biasing modes. And based on the previous work, we concluded that the asymmetries are based on the short circuit resistor AS1 and AS2. Further, the resistive elements in the N-well are not matched because the resistive elements, or both outer resistive elements, are restricted spatially by PN junctions to the side and not only to the bottom, which is the case for the inner two resistors. In turn, the resistance value, which is modulated by the junction field effect, exhibit another strength for the inner and outer resistors. So we know how the sensor shouldn't look like, and we try to imagine what can we do to improve the symmetry, and we ended up with a really simplified structure with only 3 contacts. But in this case, the annual resistors are identical and will be modulated by the junction field effect in a similar manner. We call this device the 3-contact vertical Hall element. It has 2 biasing contacts and 1 sensing contact, and you can consider it as a magnetic field dependent voltage divider. To create a 4-contact device, we just connect 4 identical 3-contact elements by connection lines of identical resistance into our novel fully symmetric vertical Hall sensor. The outermost contacts are used for the interconnection, whereas the 4 inner contacts are used for sensing and biasing, enabling again 4 different modes of operation, but this time each mode is equivalent. The state-of-the-art sensors, as well as our novel fully symmetric device, have been fabricated using a high voltage CMOS technology. A schematic cross-section and a micrograph of the 3-contact vertical Hall element is shown on the right. We also put a metal line on top of the devices, which enables us to generate an in-plane magnetic field for testing. The devices have been fabricated on an 8-inch wafer with 48 reticles, and each reticle contains a test chip with a 5-contact state-of-the-art device and our novel fully symmetric sensor. The offset and sensitivity characterization have been performed at the wafer level. To calibrate the sensitivity of the devices, reference structures have been assembled and characterized in our Helmholtz coil setup. The offset voltages for a representative state-of-the-art concept and for our novel fully symmetric device is shown at the right. The offset characteristic for the 5-contact device reflects again the asymmetric bias condition of the individual modes. In more detail, mode 1 and 3 are dominantly linear, whereas mode 2 and 4 have a strong quadratic contribution with opposite signs. In contrast, for our fully symmetric vertical Hall sensor, all modes are strongly linear with similar pairwise characteristic and similar absolute magnitudes. The offset characteristic can be modeled accurately with the 2nd-order polynomial. The single mode coefficients for both devices and the average of them after current spinning are shown on the slide. The linear coefficient as well as the quadratic coefficient have the same order of magnitude for both devices. However, after current spinning, the average is strongly reduced for our fully symmetric device. In more detail, the linear coefficient A is reduced by a factor of 7, whereas the quadratic coefficient after current spinning is reduced by a factor of 18. Concluding, current spinning is more effective for our novel device, which is a result of the improved symmetry of the device. The Hall response as a function of the magnetic field is shown on the right. We extracted voltage-based sensitivity of 17.2 and 11.6 millivolt per volt Tesla for the 5-contact device and for our novel symmetric device respectively. To calculate the current-related sensitivity, these values have to be multiplied with the input resistance of the devices, and we extracted values of about 46 and 59 volt per ampere Tesla for the 5-contact device and for the fully symmetric device respectively. Within the last slides, I'd like to present the wafer level evaluation of both devices. First, we'll focus on the residual offset distribution over the wafer. The average over the wafer is indicated by a solid line, whereas the standard deviation is indicated by dashed lines. In contrast to the 5-contact device, with an average of 145 microvolts and a standard deviation of 122 microvolts, our novel device has an almost zero offset with a standard deviation of 34 microvolts, about half of which is due to the experimental setup. Further, the power consumption of the novel device is 2.4 milliwatt, which corresponds to a reduction of 47% compared to the state-of-the-art device. As mentioned before, the voltage-related sensitivity is decreased by 32% compared to the state-of-the-art. However, the current-related sensitivity is increased by 28% compared to the state-of-the-art. So finally, we can calculate the equivalent magnetic offset field of both devices by the ratio of residual offset and sensitivity. Compared to the state-of-the-art device, the residual offset of our novel device is, or the residual equivalent offset field is strongly suppressed. And again, the relatively high standard deviation of our novel device is due to the accuracy of the measurement setup. So let me conclude my talk. I presented the fully symmetric vertical Hall sensor with an inherent symmetry equivalent to planar Hall devices. Thereby, we can reduce the residual offset after current spinning significantly compared to state-of-the-art concepts. Moreover, the power consumption of our novel device halves the power consumption of the state-of-the-art device. The reason why we still have an offset are resistive mismatches introduced by the fabrication process. Combined with nonlinear effects like the junction field effect, the symmetry of our device is slightly distorted. Nevertheless, we believe that our fully symmetric vertical Hall sensor offers a solution for the existing problems of high offset and high power consumption in the field of vertical Hall sensors. Thank you for your attention.